17. That's better. I can't hear myself. Perfect. All right. So chapter 17, we talked about electrochemistry, and we started out talking about really redox reactions in general, which again are oxidation and reduction reactions. Again, they always do occur together. So something is getting oxidized, something else will get reduced. Oxidation, one of the definitions is basically losing electrons, while reduction is gaining electrons. We could really make that decision as to what is happening based on the oxidation number or oxidation state of elements from, say, the reactant side to the product side. And as we talked about, you could use a simple number line if you're not sure to help you decide, what is being oxidized, what is being reduced. If you look at the oxidation number or state of an element on the left-hand side of the arrow to the right-hand side of the arrow, and it's getting more positive, so it's kind of moving in this direction on the number line, that would mean that it is going through oxidation as it is losing electrons, which then means it has more protons than electrons, so it becomes more positive. And if you look at the oxidation state from left to right of the arrow there, and it's kind of moving in this direction, the more negative side or moving towards the negative side, then that thing is going through reduction. Again, that would signal that it is gaining electrons and becoming more negative and being reduced. Remember that when you're asked oxidation and reduction, that is a different question than what is the oxidizing agent and the reducing agent. So again, the agents are basically opposite of their name. So the oxidizing agent is the substance that gets reduced, and the reducing agent is the substance that gets oxidized. Again, they're called that because pretty much they cause that effect in the other species that is present. So make sure, again, you don't get that confused. We went over how to balance redox reactions in acidic and basic solutions. And remember, we use sort of the water method there, which is we do split it off into its two half reactions. We balance all the elements other than hydrogen and oxygen, like normal with a coefficient if necessary. After you do that, then you can really focus in on oxygen most of the time. And we balance the oxygen again by adding water to the side that needs the oxygen. And then to the opposite side, we will add 2 H pluses for every water that we add, again, so that we're not short hydrogens at the end of the process. Also, as I mentioned, if you're starting out sort of unbalanced in terms of hydrogen on one side of the half reaction versus the other, you could just add some H pluses to the other side to balance out the hydrogen. So you could kind of use that H plus to balance out hydrogen if you're kind of unbalanced to begin with as well. Once you do that, then you're going to add some electrons. And again, we add electrons always to opposite sides in the half reaction so that they can completely cancel out. And we add it to whichever side will need a negative number to balance out the overall charge on both sides of the arrow. Again, they don't have to equal 0 on both sides of the arrow, but they do need to equal the same number. So we do that. Once you've done that, then you could add the half reactions back together. Before you do that, obviously the electrons do need to be the exact same number in each half reaction. If it is not, then you need to multiply either one half reaction by a number or even both of them by a common number, because the electrons should always be completely canceled out. Once you add them together, it cancels out the electrons. You also can't cancel out or reduce anything else that may be there that are opposite sides of the arrow. And at that point, you will have a balance in acidic conditions. And you'll know that because on one side of the arrow there, you'll see H plus by itself, and that will tell you that it is basically balanced in acidic conditions. If you want to do basic, the easiest way to do it really is sort of balance it acidic. And at that point, you will add OH minus to both sides, and that OH minus is equal to the amount of H plus that you have. Those guys will then come together and make water. And typically speaking, you usually will have to reduce down some of the waters as well. And you'll be then left with an equation that has OH minus in it, which will tell you that it is basically being balanced in basic conditions in this particular case. We then got into really what the chapter is mainly sort of about, which is galvanic cells. And galvanic cells are really redox reactions that occurs. A traditional one can be built in beakers in the laboratory. One side's your anode, and your anode is where oxidation occurs. Your other side is your cathode, which is where reduction occurs. And really, when you build this, you have some type of metal electrode in the solution. So, for example, that's zinc. And if that's zinc, then you would also have zinc ions floating around, also probably a negative ion as a spectator ion, like nitrate or sulfate or something like that, maybe floating around with it. This gets connected to like a voltage meter to the other side, where you also will have a solid electrode, maybe copper. And you will then have copper ions floating around in the solution. And again, it would also have sort of a negative ion with it. What connects both of these sort of components or sides to the galvanic cell is our salt bridge. And the salt bridge usually will have some type of electrolyte sort of solution in it. And, like potassium chloride, I think was in that picture we were looking at. And basically the idea there of the salt bridge, put some cotton in there so it doesn't fall out. The idea of the salt bridge, as we talked about, is it allows really the electrons to continuously flow from the anode side to the cathode side. And it does so because there's really a potential difference. You can almost think of the cathode side as being a little bit more positive to help pull the electrons towards that side. Again, without the salt bridge present, what's going to happen is, as we talked about, basically as the electrons come this way, it's going to combine with, say, the copper, and that copper positive ion would come out of solution. And again, on the right-hand side, what's going to happen is we will get all these zinc guys jumping into solution when they lose their electrons and becoming more positive. So if you don't have that salt bridge there, what you're going to get, as we talked about, is sort of a buildup on the anode side of a positive charge because all of those positive ions are dropping into solution. On the cathode side, you'll get a buildup of really negative charge because all the positive guys are leaving the solution. And that's going to be really bad for our negatively charged electrons because it's not going to want to go anywhere near this side because it's now built up too much of a negative charge. Plus, this side is now really positive, so it doesn't even want to leave. And that's going to stop, obviously, the flow of electrons from going from one side to the next. So with that salt bridge, what that allows us to do is, even though we're losing some positive guys here, we're still going to be able to drop in some positive ions here to kind of keep the positive charge up. While we are gaining a lot more positive over here, we'll drop some negative ions into this side. And again, that will keep the buildup of charge incorrectly from happening on both sides of the galvanic cell. We could calculate the cell voltage, cell potential by taking E of the cell is E of the cathode minus E of the anode. And remember that we do use this equation here with the minus sign if we do not change the SRP values that we find in the table. So SRP is our standard reduction potential, which are those half reactions which have our voltage values. And they are all written, for example, as reduction reactions. Again, they're reduction reactions with their E. And that means in a galvanic cell, really, you'll have one of those reactions incorrectly written. It should actually be the oxidation reaction, which means you should reverse the sign on the E. But if you don't want to reverse the sign, as we talked about last time, you would use the subtract there, and that will change the sign for you. If you do want to change the sign yourself, as we talked about for the anode reaction, basically, then you should add, not subtract. So again, as I mentioned before, just decide sort of which way you want to do it maybe, and just roll with that. If you are, though, writing an equation, an SRP type reaction or a reaction, you should have the proper E sign with it. But if you're just simply looking for what the cell voltage is, you can basically do that. We also saw cell diagram, which is sort of a shorthand for a galvanic cell, where you have a couple of things here, which is your anode side separated by the salt bridge. And on the right-hand side, you have two things, which is your cathode. And sometimes you may have more than two things, especially if it's a gas or something like that. So you may have a electrode mentioned. Remember how this sort of works is kind of reactant product, if you need to kind of turn that into sort of the equation. Any questions on any of that stuff we talked about last time there? All right, so I think we left off with this example, so why don't you give it a go. Galvanic cell consists of magnesium electrode and 1 molar magnesium nitrate and a silver electrode in silver nitrate. Calculate the standard EMF of the cell, basically the cell voltage. Okay, so let's take a look. So the other thing we talked about obviously last time as well is if they don't give you sort of a reaction or anything like that, or tell you how it's happening, and they just kind of like in this problem tell you we basically built a galvanic cell of these two things, you can use the SRP values, which are what we see down here, to help you decide which one should be your cathode and which one should be your anode. And the one that is more positive should be your cathode, which in this case looks like this guy. So we know the silver here should be our cathode. By default, obviously, our other guy there would be our anode. And that means really if you're just answering this question, which is basically what is the cell voltage, you can go again right into your equation here. And in this case, I'm not going to change the sign, so I'll just put it in there, and that's the cathode, which would be 0.8 volts minus our negative 2.37 volts and 317, I think, for this particular guy here, and that would be our cell voltage in this case. Now, again, what that means technically, if you kind of wanted to fix it up here and get the overall reaction, we do have this guy here, which is written correctly. This guy, which is our anode, technically that equation would need to be reversed if we wanted to sort of put it together properly here. And that means since I did reverse it, this would then become positive 2.37 volts. And remember that we really can't add this together. We would need to multiply the top guy by 2 to get the same number of electrons. And also remember what we talked about is it does not get multiplied by the E, or the E doesn't get multiplied by that number. So we don't multiply it by that number. That would then give us our balanced equation where our electrons would cancel. It gives us our 2 silver plus our magnesium goes to our 2 solid silver and our aqueous magnesium here, really. Solid and aqueous. And at this point, if you did want E of the cell and you did change the sign like I did here, you would just, again, add those together and not subtract because you already changed the sign and you would get your 3.17 volts. So again, you could really do it either way, whichever way you want to do it. They should come out the same. Again, just don't mix them and do both together. Any questions on that one there? All right, so let's talk a little bit about cell potential, electrical work, and free energy. The work that can be accomplished as the electrons basically go out through the wire depends on the push behind the electrons, and that's the thermodynamics. So a volt is equal to a joule divided by a coulomb of charge. So 1 joule of work is produced or required there when 1 coulomb of charge is transferred between 2 points, sort of in a galvanic cell. So when we cell produces a current, the cell potential is positive, and the current will do the work, like run a motor or something like that. And what we end up getting in terms of our thermodynamics is the maximum amount of work will actually be equal to our delta G, which is our Gibbs free energy, which is that energy available to do some type of work. So we can relate our cell voltage to our thermodynamic equation through a couple of relationships here. Let's talk about those here in a second here. So the first one is here, we can take our delta G and is equal to minus NF E of the cell. And obviously here, that's going to be our E of our cell is going to be our cathode minus our anode. The F is Faraday's constant, which is 96,500 or 96,487, whichever number you like. We'll go with that number. And if we substitute this in with our sort of delta G equation that we had with our equilibrium, we could actually get a relationship between our cell voltage and our equilibrium, which is this guy right here. E of the cell is equal to RT NF natural log of K. This R is the one that involves energy, so that's the 8.314 version of R. T is our temperature in Kelvin, and it's the moles of electrons. And F is still our constant there, our Faraday's constant. Now, when we talk about N, or the number of electrons, it is the total number of electrons that have been transferred, say, from your anode side to your cathode side. So a mistake sometimes people make, for example, is if we have this equation here where we have something gives up a couple of electrons, then a couple of electrons get added to something. And you want the N in this sort of situation. N in this case would equal 2 only. You do not add them together. Those are the same electrons going from the anode to the cathode. So N here would be just the 2 that are really being lost by the anode part, or the oxidation part in this case. So sometimes people will add those together, and again, that would be incorrect. So when you do calculate 2, that, or N, that is how you should do it. Now, if you are at 25 degrees Celsius, really R, T, and F are all constants. And you can reduce down this equation here to one of these two other equations on the bottom, which is basically 0.0257 volts divided by N, natural log of K. Or if you like the base 10 log there, you can go 0.0592 divided by N times log of K. If you don't want to worry about either of these equations, just remember this one and just put the numbers in, and it'll come out the same. So you could just plug them all into that equation right there that's in the box, and you'll have it. This is our triangle of death here of thermodynamics and electrochemistry. So if you have E of the cell, you could get to delta G versus this equation. Obviously, if you have E of the cell, you could get to K, or if you have K, you get to E of the cell. And then our thermodynamic relationship between G and K that we saw in the previous chapter. So when we look at these sort of equations here, and sort of the relationship, the delta G is equal to minus NF E of the cell. This is why, for example, if we have a positive value for E of the cell, F and N are positive numbers, which means you will always hit a negative value for delta G. And that means that the reaction should be spontaneous at that point. So that's why a positive cell voltage is good in most cases, because it means reactions should occur. It should be spontaneous. And because it's spontaneous, it means that the reaction is heading from reactants to products, which means you're probably making more products. And that would result in a K value that's greater than 1, or a large K value, because you'll have more products than reactants at that point. Opposite is true. If you end up with a negative cell voltage, that negative plus the negative right here will turn your delta G into a positive number. And that would mean that the reaction would be non-spontaneous the way it's written. And because the reaction is non-spontaneous, that means pretty much everybody's going to stay at the reactant side, and you would have a lot more reactants than products. And that would result in a lower value of K, or a small value of K, because of that. If your cell voltage equals 0, then K would equal 1, and your delta G would equal 0. And it's a toss-up as to which one would be favored. Any questions on those relationships there? All right, so let's take a look at one here. Calculate delta G for the following reaction, and is it spontaneous? Okay, so let's take a look. So we do have an equation here, so we can see what's going on. We got copper there going from +2. We got iron, which is 0. Copper here on this side is 0. And our iron over here is +2. So the copper is getting reduced as it is going from basically +2 to 0 copper. So it's being reduced. And the iron here is going from 0 there to +2, and it is being oxidized. So in this case, our copper would be our cathode, and our iron here would be our anode in this particular case. Now we want to calculate delta G, so we go delta G is equal to minus NF E of the cell, basically. So we'll start with the E of the cell, and that's going to be our cathode minus our anode. Once again here, I'm not going to change the sign. If you change the sign, obviously you would be adding instead of subtracting after you change the sign. That's what the subtract's going to do for me. It's going to change the sign. And when I do that, that will give me an E of the cell here of, looks like 0.78 volts. Now, N in this case is going to equal 2, as that is what we see here. Once again, we're not going to add them together because they are technically the same electrons leaving the anode coming to the cathode. And F is a constant, which is our 96,500 joules per volt per mole here. And that is going to give us what we need in this particular case. So if we pop it in here, our delta G naught will equal minus 2 moles. Our Faraday's constant, 96,500 joules volt mole. And our E of the cell, which is 0.78 volts. Volts will cancel, moles will cancel, going to leave us here joules. And that's going to get us here times by 2. About 150,540 joules, which is negative. And if we want to go with delta G, which is typically in kilojoules, roughly about 150, I guess we'll call it 1 kilojoules. In this case, we divide it by 1,000. First off, any questions on that there? This reaction is going to be spontaneous or non-spontaneous? It's going to be spontaneous, right? And that's because we have a negative delta G, which tells us it's going to be spontaneous. By the way, we should know actually it was spontaneous just by the E value, right? The E value there is positive, which should always give us a negative delta G. So just from that value, you can determine that it should be spontaneous, really, in that particular case. Any questions on that one there? All right, so the next question is, will 1 molar nitric acid dissolve gold metal to form 1 molar gold-3 ions in solution? Okay, so let's take a look here. So our cathode in this case is, which one? Cathode is the nitric acid in this case, yes. So our cathode is nitric acid. This would be our anode in this case. And you may be asking, why is that? Because the gold is more positive, right? But in this question, it's asking, will nitric acid dissolve gold metal, which is this guy, to make gold-3, which is this guy? So you got to read the question, and we can see from gold here, it needs to be actually reversed and be the anode in this case. So again, if they give you information on how the reaction is taking place, you have to actually look at it, yeah? Or if they give you an equation, you have to look at it and see what is being oxidized, what is being reduced. Again, you only go with the more positive one if there is no information on how it's reacting. But in this case, it told you basically how the reaction is going to take place. So that means that technically speaking here, we would do our E of our cell, which would be E of our cathode minus E of our anode. And in this case, 0.96 volts minus our 1.5 volts, going to give you negative 0.54 volts. really from that negative value for E of the cell, it will tell us that this reaction is non-spontaneous. That's because when we go into our delta G minus NFE, we will have a negative here along with a negative here, which will then turn our delta G into a positive, which will tell us it's non-spontaneous. So this will not actually happen. Yeah. Question on that. You could actually calculate delta G and get the value if you wanted to as well, but the result of it will be a positive value, which would tell you this will not happen in this case. So no. This is how they test sometimes to make sure you really have gold. Like you go into a pawn shop, yeah, they get the nitric acid out, they put it on your little jewelry or whatever it may be that's gold, and if it's still there, you're good. If it disappears or doesn't stay there and reacts, then you're not so good. It's not real gold. So that's sometimes how they used to test it. Any questions on that? So again, really important in here, sometimes people always just roll with the more positive, it's the cathode. Again, you only want to do that if there's no other information given to you. But if they do tell you how it's happening, you do need to kind of look at it, what's going on. Any questions on that there? Okay. All right, so why don't you try this one here? What is the equilibrium constant for the following reaction? Okay, so let's take a look. Obviously, we're looking for the equilibrium constant, so we probably should use the one that has that in it. So that's going to be our RT-NF natural log of K. Here we do have obviously R, which is a constant, 8.314. We do have our temperature, which is 25 degrees, which if we add our 273 to it, should be 298. In this case here, F is also a constant, 96,500 joules per volt per mole. We then have our N, which will be 2 in this case. So we do need to basically calculate our E of the cell here. And once again, in this particular problem, because it will not always obviously nicely tell you which one's being oxidized, which one's being reduced, we do have the equation given to us. And the oxidation state here of iron is +2, 0, 0, and +1. So when we look at the iron in this particular case, it is going from +2 to 0, which is moving in that direction, which means it's being reduced. And the silver here is starting at 0 and ending at +1, which means it's becoming more positive and going through oxidation. This is different than the SRP value that we would choose for our cathode in this particular case. So again, you do need to make sure you look at the equation and see what's being oxidized, what's being reduced. That is why our iron, which is being reduced, is our cathode in this case. And our silver, which is actually being oxidized, is our anode. That's going to allow us to calculate our E of our cell here. And again, taking our cathode minus our anode. Once again, I'm not going to change the sign, so I'm going to subtract. So we're going to go with our cathode there, which is iron, which is minus 0.44 volts, minus a 0.8 volts. Going to get us there, looks like 1.24, negative 1.24 volts. By the way, we already know at this point with a negative value for E, this reaction is spontaneous or non-spontaneous. This reaction is going to be non-spontaneous. That means that when we calculate K, we should end up with a small value, right? So again, those things should agree. So let's see if we get that. We'll have a negative 1.24 volts is equal to our 8.314. Our temperature in Kelvin divided by our N, which is 2 moles, and our Faraday's constant there. And natural log of K. So we can clean up here on the right-hand side, 8.314 times 298 divided by 2 divided by 96,500. Going to give us negative 1.24 volts is equal to 0.012837 natural log of K. We then could divide that to the other side. And if we do, we will end up with about 90 minus 96.5945 equals the natural log of K. At this point, to get rid of the natural log, we're going to E both sides there. That's going to get rid of the natural log. We are not going to change the sign or anything that's on there. And we'll end up with like a 1.1 times 10 to the minus 42, which I would say is a small value of K, which makes sense with our negative value for E of the cell, which would ultimately give us a positive value for delta G if we calculated that as well. Any questions on that there? Now, if you use one of those kind of rounded formulas, the 0.0257 or 0.0592, you might get a slightly different answer in terms of how you rounded it. The back part here should be the same, but this part might be slightly different depending on where you rounded there when you did the E to both sides, but it should still be in the ballpark. Any questions on that there? All right. So let's talk a little bit about the effects of concentration on the cell voltage. And once again, we can have situations where maybe we're not under standard conditions. And when we're not under standard conditions, we could put together some of our thermodynamic equations along with our sort of cell voltage equations. And we get what's referred to as the Nernst equation here. And the Nernst equation is this guy right here. And they're all the same type of things. This is, you could kind of think of it as the cell voltage there under non-standard conditions. This would be your cell voltage under standard conditions. And that basically is your, like we've been doing, your E of your cell is your E of your cathode minus your E of your anode in this particular case. The rest of these guys here are pretty much identical to what we just used. So the 8.314 version of R, the temperature in Kelvin, the moles of electrons and Faraday's constant. Q is our normal Q calculation, which should be our products divided by our reactants. And again, we would still use, obviously, the coefficients as the exponents. So this is an equation that you would use essentially under non-standard conditions. So if you're dealing with pressures and it's not 1 atmosphere, if you're dealing with concentrations and they're not 1 molar, or really even temperatures not 25 degrees, again, you would want to use this equation here. It also can reduce down at 25 degrees Celsius into these reduced versions like we saw earlier. But again, if you don't want to worry about those two bottom ones, just plug everything into the top one, the middle equation there, and you'll be fine along the way. This, by the way, is where we got the other equation that had the equilibrium constant, because at equilibrium, E would equal 0 and Q would equal K, which would give you 0 is equal to E naught minus RT NF, natural log of K. Bringing this entire thing to the other side gives you the equation we just used, the RT NF, natural log of K. Also, why there is no negative on that one is basically because that's why that is when you rearrange it. So sometimes people want to always put the negative into that one we just used. And again, the negative actually are just the subtract button actually is on the Nernst equation here. Any questions on that there? All right, so why don't you give one a go here, see what you got going on. Will the following reaction occur spontaneously at 25 degrees if the iron 2 concentration is 0.6 and the cadmium concentration? Okay, so let's take a look. So we're looking to see if this reaction can occur spontaneously. The first thing that you should see is these concentrations are not 1 molar, which means this is non-standard conditions, basically. And that means that you should be using the Nernst equation, which is our E is equal to our E naught minus our RT/NF natural log of Q in this case. So we do need to find a few things here. So first off, we want to figure out what is being oxidized, what is being reduced. We are given an equation, so we need to look at it and see what's going on there. So +2 for the iron, 0 there on the other side, 0 for the cadmium on the left, and +2 on the right. So cadmium is going from 0 to +2, which means it's becoming more positive and is being oxidized. So our cadmium here would be our anode. Here, the iron is going from +2 to 0, moving in the negative direction, and that means that it is being reduced, and that would be our cathode in this case. Again, opposite of basically the numbers there. So we can calculate our E of the cell under standard conditions by taking our cathode minus our anode here, and putting those numbers in will give us negative 0.44 volts minus a minus 0.4 volts. And that's going to get us here minus 0.44 minus a negative 0.4. There we go. Gives us a negative 0.04 volts, right? So under standard conditions, this reaction is non-spontaneous, right? Because it's got a negative voltage. So what we're seeing here is if maybe playing with the concentrations of our anode and cathode, can we maybe make this non-spontaneous reaction actually become spontaneous by playing with the concentrations? So we have this now. R is a constant. Our temperature here is 25 degrees, so 298 on that. And our R obviously is still 8.314 joules per Kelvin per mole. Our N in this case is going to be 2, as it's iron 2 and cadmium with a +2 charge, which means there was 2 electrons if you broke that up into the half reactions. Again, you can see that with the cadmium, just it would have 2 electrons basically happening there. And the same thing with the iron as well. So if we have our 2 there and our F is also a constant, 96,500 joules per volt per mole, that means that really we do need to calculate Q in this case. So Q would be our products over our reactants. And in this case, just like normal, it is going to be the cadmium over our iron 2. Again, these guys are solid, so like normal, they would not be included in our Q equation. So popping in our numbers there for cadmium, 0.01 divided by 0.6. And that's going to get us 0.01 divided by 0.6, 0.01667. At this point, I think we got everything we need. So our E here is going to be our negative 0.04 volts minus our R, which is 8.314. Our temperature, which is 298. Our N, which is 2 moles, and our F, which is 96,500 joules per volt per mole. Natural log here of Q, which is what we just calculated there, 0.01667. All right, so I'm going to clean up the right-hand side, I think, of the minus sign there. So I'm going to take the natural log of my 0.0166 number. I'm then going to multiply it by 8.314 and multiply it by 298. Then I'm going to divide it by 2 and divide it by 96,500. And that's going to give me a negative 0.04 volts minus a negative 0.052559 here, volts basically. And if I add now those together, we'll go negative 0.04 minus my answer there, going to get us a 0.013 volts. First off, any questions on the calculation there? Is this reaction spontaneous? This reaction is spontaneous. You didn't get a lot of voltage, but you got a little bit of positive voltage in this case. Again, the positive voltage here will give us a negative delta G. And this reaction will be spontaneous barely by having a little bit of positive voltage basically happening. Any questions on that? So this illustrates that if you have a reaction that's maybe non-spontaneous, you can maybe play with the concentrations and turn it into it being spontaneous, maybe just a little bit, like in this particular case. Any questions on that one there? All right, let's try this one here to finish it up on, I think. For the following, don't worry about the balancing, just calculate E and K there for this particular guy. Okay, so let's take a look. Again, we're looking for E, which is obviously our E of our cell. So our cathode minus our anode, just got to identify which one's which. We also are looking for K. So once again, if you can't remember the first equation that we used for K, but you can remember the Nernst equation, again, you can derive that equation from it because obviously we're at equilibrium at this point. We will know, as I just mentioned, E would equal 0 and Q would equal K, which would give you 0 is equal to E of the cell minus RT NF natural log of K. Take this whole entire part and basically add it to the other side. Will give you the equation that you need, which is the RT NF natural log of K. So again, you could get that other equation from the Nernst equation. So we'll start with what's going on here. If you're scared of this one, you can skip it and just look at this guy, which is +2 and +3. So definitely the chromium here is becoming more positive. So it is being oxidized, which means this would be our anode and this would be our cathode. Again, in this case, if you just skip that part, you got lucky because the numbers worked out that way as well. So you'll be in good shape. By the way, in case you're curious, that's a -2, that's a -12, that's a 10, that's like 2.5 or something like that. And over here is a -2, 6, a 4, and a +2, right? So it's barely getting reduced a little bit in that particular case. So we'll calculate our E of our cell here. We'll take our cathode, which is 0.17, minus our anode, minus 0.5. Going to give us our cell voltage here of 0.17 minus negative 0.5, a 0.67 volts. So at this point, we could then go into our equation here. We have our E of our cell, and in this case is going to be 2, it looks like, right, in this case. So it should be 2 in this case. And that would then mean that that's everything that we need. So we got 0.67 volts is equal to 8.314. Our 298 here, which wasn't given to you, but we'll assume it's 298, I suppose. And we got 2 moles and our 96,500. And obviously our natural log of K as I run out of room over there. So I'm going to clean up kind of before the natural log part there. That's going to give me 8.314 times our 298 divided by 2 divided by 96,500. That will give me 0.67 volts is equal to 0.012837 natural log of K. We're going to divide that to the other side. Going to give us a 52.192 equals the natural log of K. And we're going to E both sides. Again, not changing any signs. And if we take the E of that, we will end up with like a 4.6 times 10 to the 22, which is a large value of K, and that goes okay with our positive cell voltage, which means we should have a negative delta G, which means the reaction should be spontaneous, should be heading to the products, and we should have more products than reactants and a large value of K. Again, all those things should agree with each other when you kind of look at them. Any questions on any of that there? All right, we're